In this video, we're going to learn how to solve exponential equations. And there's two ways that I'm going to teach you that you can solve exponential equations. And the first way is kind of the most clever way, and it's by equating exponents. And it's really pretty clever once you see how it works. Basically, what's going on here, if you have b to the power x and it's equal to b to the power y, so long as the base is assumed to be bigger than 0 and it's also not equal to 1, what we'd have to say is true. If this side and this side are going to be exactly the same, it's got to be true that these exponents are the same. So what we would then say is just equate the exponents. X has to be equal to y. So this is kind of a nice little trick, and we'll do a couple of examples of that. If we can't solve by equating exponents, the surefire way of going about solving an exponential equation is by taking logs of both sides. So we're going to solve by taking logs of both sides. So let's actually check out a couple of examples where we're going to do that first process, just equate exponents. So for number 1, let's call it example 1. For example 1, what we're going to do is try to solve when does 4 to the power 3x equal 8 to the power x plus 1. Now the first thing you should notice right away is that the base 4 is not the same as the base 8. So you cannot simply just do 3x equals x plus 1. That's not going to work. You have to make sure, you have to guarantee that these bases are the same first. So let's go ahead and see if we can figure out, is there a way we can rewrite 4 and 8 so that they are the same base? And hopefully you're thinking, yeah, there is, because 4 is the same as 2 squared to the power 3x, and 8 is the same as 2 to the third to the power x plus 1. So all I've done in that first step is I've rewritten the bases 4 and 8 as 2 to the second or 2 to the third. Now hopefully you remember your exponent properties. You know that 2 squared to the power 3x, you're really multiplying those exponents to make it 2 to the 6x power. And here you have to multiply the exponents too. Now of course you'd have to distribute the 3 to the x and to the 1, and that's a classic mistake students make when they get a problem like this. They forget to distribute that exponent for 2. So it's going to be really 3x plus 3 if you distribute. Now we've set it up so that the bases are exactly the same, and I can apply that first method where we can just equate exponents. So I'm going to go ahead and take the 6x and the 3x plus 3 and equate them. Now we're in, all of a sudden, Algebra 1 land, and we can just subtract 3x and we get 3x equals 3, and of course that would mean then x equals 1. It's a very good idea to check your final answer. So if we plug x equals 1 into the original exponential equation, we'd have 4 to the 3 times 1 power equals 8 to the 1 plus 1 power. That'd be 4 to the third should be equal to 8 squared. And 4 to the third is 64, and of course 8 squared is 64. So I know we're in good shape. Let's do another example. Example 2. I'm going to solve when does 2 to the 4x power equal, make that a better x, 2 to the 4x equals 32 to the power x minus 1. Now once again, I'm making this a little bit more challenging because 2 and 32 are very clearly not the same base, and we can't break 2 down into anything else. That's already prime, but we can break 32 down into 2 to the 5th, right? Which is nice because it's the base 2. So I can rewrite 32 as 2 to the 5th, all raised to the x minus 1 power, and we don't have to change 2 to the 4x. In fact, we want to keep that base anyway. What I need to do though is rewrite this as 2 to the 4x, and then don't forget to distribute that power of 5. So it's going to be 2 to the 5x minus 5 power. Now we're in good shape because the bases are identical. I can then equate these exponents. So I can just set up 4x equals 5x minus 5. And once again, we're in good shape because it's just a simple linear equation to solve. If we subtract 5x, we get negative x equals negative 5, which of course means x equals positive 5. It's a good idea to check. If we were to check x equals 5, then it would be 2 to the 4 times 5 equals 32 to the 5 minus 1 power. So this is 2 to the 20th equals 32 to the 4th. Now that's going to be a really big number. A quick thing I could do is rewrite 32 as 2 to the 5th, and then of course that's raised to the 4th. And if you multiply the 5 and 4, you get 2 to the 20th. So 2 to the 20th equals 2 to the 20th, and I know we're in good shape. Let's go on to another method where we're not going to necessarily be able to equate exponents. Let's look at example 3. Let's say we're trying to solve when does 3 to the x power equal 8. We might be saying, all right, let's see if we can equate exponents. We can rewrite 8. That's the same as 2 to the 3rd, and we have 3 to the x. Oh, we're kind of stuck though because the base 3 and the base 2 are clearly not the same. The method we just used is not going to work for us in this particular example. So it's a nice try, and it would be nice if it worked, but it's just not going to work. When you can't equate the exponents because the bases won't match, you're going to need to take either the log or ln of both sides. Now, you'll kind of know when to use one or the other. In a couple examples, we'll kind of know for sure we'll want to use log over the ln or vice versa. It's really up to you in this particular example when the base is 3. Here, let's just use the common log. So what I'm going to do is I'm going to take the common log of 3 to the power x. So I'm actually taking the log of this entire side of the equation. So if I log the left side of the equation, I have to log the right side, which is just 8. So I'm going to take that and make it the log of 8. Now there's a nice property we can use here to bring x out of the exponent. If you remember from the last lesson, that's called the power rule. We can bring down the x in front, and it's no longer an exponent. It's just going to be x times the log of 3. Now remember, the log of 3 is just what you raise 10 to get 3, and it's supposed to be equal to the log of 8. So I have x times this number. All I have to do to solve this is divide by the log of 3. So my answer for x is just the log of 8 over the log of 3. Now if you put that into your calculator, and I'm going to have to grab it real quick. If you put that in your calculator, and just make sure when you put that into your calculator, you're going to type in the log, and that'll give you the parentheses 8. Make sure you close those parentheses off. And then you can hit the division button and type in the log of 3, and just make sure you close parentheses. So double check that you get this value. If you round to 2 decimal places, I get about 1.89. So if we check, I had 3 to the 1.89 power. Should be pretty close to 8. Now remember, we rounded, so this may not work out to be exactly correct. But if you put that in your calculator, 3 raised to the 1.89, I get about 7.98 to 2 decimal places, and that's pretty close to 8. Again, the exact value, right, the exact answer to this problem would be the log of 8 over the log of 3. So if I ask you to approximate, this would be your answer, but the exact answer is that one, and I would probably want at least both. You know, I would definitely want to see that original exact answer, log of 8 over log of 3. Let's look at another example. Let's make this example, I think we're on example 4. This one's going to be a little bit more exciting. We have 10 to the power 2x minus 3 plus 4 equals 21. Now, before we do taking logs of both sides or anything like that, you want to always first isolate the power. So you want to make sure you get the power by itself, and in this particular problem, the power is this guy, 10 raised to the 2x minus 3. So the first thing you want to do to both sides is minus 4 on both sides of the equation, which would just give us 10 to the 2x minus 3 equals 17. Now, there's no way of rewriting the base 10 and 17 to be the same thing. 10 is 2 times 5, 17 is prime. You're not going to be able to rewrite this. Now, you have the choice of using either the log of both sides or the ln. Now remember, when you write log, that's the common log. It's base 10. Because the base of our exponent is 10, I would definitely use the log and not choose ln, which is base e. And maybe the next example I'll show you one where you would want to use base e. So let's do the following. Let's take the log, just the common log of both sides. So we're going to log 10 to the power of 2x minus 3, and we're going to log 17. Now, just like in the last example, when you take the log of an exponential expression, you can take the exponent and bring it out in front. So what I'm going to have now is 2x minus 3, and I really should put that in parentheses because that entire quantity is being multiplied by the log of 10, and that should be equal to the log of 17. Now, guys, log of 10 is a nice number. What this really is asking is 10 raised to what power is 10, right? I mean, that's what log of 10 really means. And hopefully you know that, of course, 10 to the first is 10. So this entire number is just 1, which is awesome because it essentially just goes away. So I get 2x minus 3 times the number 1 equals the log of 17. So of course, multiplying that by 1 doesn't do anything, and we can just add 3 to both sides, and I get 2x equals, now don't be foolish here and think you can add 17 and 3. You'd have to first take the log of 17 and then add 3. So it's really just 3 plus the log of 17. And then we'd have to divide everything by 2. So our final answer, the exact final answer, is 3 plus the log of 17 over 2. Now, when I type this into my calculator, I'm not going to bring the calculator on the screen, but I want you to try this with me to make sure you're doing it correctly. When I type this in, I'm going to start by putting left-hand parentheses, typing in 3 plus, and then I'm going to hit the log button, and it's going to pop the left parentheses of the log up for me. I'm going to type in a 17, then I'm going to close the 17 parentheses, then I need to put right-hand parentheses for that one so that the calculator knows this whole thing is the numerator. Then I'm going to hit divide by 2. So try that right now and see what you get. If you did that correctly, hopefully you got to the nearest, let's go to 2 decimals, about 2.12. So if we had to check this, back into our original problem, it'd be 10 raised to the 2 times about 2.12 minus 3 power plus 4 should be pretty close to 21. Now again, since we've approximated here, it's not going to be maybe exactly correct. So if you type that in, 2 times 2.12 and then take away 3, the exponent's really 10 to the 1.24 power, add 4, should be equal to 21. I'm actually going to just type all that in, 10 raised to the 1.24, and then add 4. I do get about 21.37 is equal to 21. So again, it's not exactly right, but that's because we cut off all sorts of decimal places. We only rounded to the nearest hundredth, which really isn't that accurate. Let's do one last example, and then I'm going to ask that you try a couple on your own. So here we go. I think we're on example 5. example 5. Let's see if we can solve 20e to the 0.5x minus 6 equals 10. So if you remember from the last example, our first job is to isolate the power. Now, you might think this whole thing is the power, and you're close, but you would be wrong. You really want to isolate only the base and the exponent, and 20 is not part of the base. The only thing being raised to the 0.5x is e, okay, not the 20. So we have to actually get rid of that 20 as well. So let's first, if I'm going to remember, we're just trying to get the e to the power of 0.5x by itself. I'm going to add 6. So I'm going to get 20e to the 0.5x equals 16. Now I have to divide by 20. And that's another classic mistake students don't make, is they don't correctly isolate the power first. You have to get rid of any coefficient that's in front of that base. So I'm really going to have e to the 0.5x equal to 16 over 20, which reduces to, what is that, 4/5. So I have 4/5, and we could even maybe use just a decimal. That's exactly 0.8, right? So if we put in 0.8, that might make our lives a little bit easier, not having to deal with the fraction. So I'm going to do e to the 0.5x equals 0.8. And now we're ready to take the log of both sides. Well, I have the choice of the common log or the natural log. And hopefully right now you realize, hey, using the ln, and I know that I didn't write that very nice, if I use the ln, that's going to be good because it's base e. So let's use ln and see how that works. If I do ln of e to the 0.5x equals the ln of 0.8, what that allows me to do is bring down the 0.5x. So I get 0.5x ln e equals the ln of 0.8. And now the ln of e, just like the common log of 10, is 1 because it's asking e to the what power is going to give me e, and of course that's 1. So this just goes away. It's the number 1. So I have 0.5x equals the ln of 0.8. Last step is to divide by a half, or 0.5, and we would be done. So x equals the ln of 0.8 divided by 0.5. Instead of dividing by half, I could have also multiplied by 2. So another good way of writing this would have been just 2 times the ln of 0.8, and they should give you the same answer. When you type this in to get your approximate value, make sure you close off parentheses around that 0.8 before you divide by a half. So double check that you're doing this right. If you take the ln of 0.8 and you divide by a 0.5, you get about negative 0.4, oops, you should get negative about 0.45. So again, exact value along with approximate value there. This is what I'd like you to do now is your self-quiz. In your self-quiz, you have these 4 problems. I'll give you a hint. The first one is the only one that you can try to equate exponents. Alright, the other ones you're all going to want to take logs on. And it's up to you to maybe pick the appropriate log, or the ln, of course, right, for these. So go ahead and give those a shot, and we'll talk about them in class. Thanks for watching.